All right. Just like any other review day, if you don't have a 10 o'clock class and you'd like to stay, you're more than welcome to. We're just going to be doing the same thing for the next hour as well. So you are welcome to stay for both. We'll start off by just opening up to if you have specific questions because you worked on it this weekend. Thank you. I'm not going to go through one, two, three, four, five. I'll just open it for questions and well, we'll start there. Did anybody work on it at all this weekend? Good job. Thank you. Did it seem pretty easy compared to the last test?
I mean, I think the last test was easy.
To me, this section's a little easier. I don't know.
It's just a lot more stuff.
More random. Hey, know this formula. Know this. Yeah. And you don't get formula charts, and you don't in this class or pre-cal or cal. You won't ever get these like formula charts like you used to. So it does make it a little tougher, but
it is easy, but it's just a lot more.
Sure, that's fair. All right. Anybody have any questions or places to start? Otherwise, you're just wasting YouTube's time.
On review, I can do homework. Just on review.
Yeah, no, homework's fine. Because the homework is harder for sure.
Can we start with number 7?
Sure. On which one? On the old one or the new one? If you didn't get this new practice test, I just printed a bunch of practice problems from section 3 and 4. This is only chapter 3. I need to pull up chapter 4 as well. But yeah, if you didn't grab it, I put it over there. Cool. There we go. Chapter 4, chapter 3. Perfect. All right. So you're saying which one?
Number 7.
Oh, sketching transformations? Yeah, that's a good. What's up? Because it's giving you it. Oh, that's a good question. That's a really good question worth answering, like thinking through on your own. This is slightly different than some of the other ones we've seen in the past. Because there's already stuff on the graph, right? So you asked the question, why is there stuff on the graph? I leave that for you. Why is there stuff on the graph? What did they not give you? Okay, it's even more than that they didn't give you. You're right, you don't know the exponent. But you don't know even, they literally haven't given, so like, what if they just gave you that problem right there, zoomed in? Or, right, what do you not know about anything? So if this is the only problem you have, you can only literally say one thing. What's the one thing that you can say? You can't say the y-intercept. There's only one little thing that you can make comment on if this is the problem in total. Yeah, that's what you can say. That's the only thing you can say. It moves up by 1. So what did they not give you here? Okay, that goes with the exponent. They didn't give you the slope, you're right, but they also didn't give you the exponent. So there's this bigger thing that they didn't give you. That's it. They didn't give you f of x, right? So the answer to your question, which is they already gave you some stuff on the graph, is because the reason they gave you stuff on the graph is because look at this. Usually, at least in the past, they've given us the parent function. They've said also f of x is, like you said, a linear function if you're looking for slope, or an exponential function if you're looking for an exponent. Usually they give you like an f of x, right? They didn't give us an f of x. Well, they did. They just gave it to us in a different format. They gave it to us in the graph format, not the equation, not the table. All the different, there's one, not the little mapping diagram that looks like that, right? They gave us the graph format. So you're right. We can just use those points to do it. So what is the only thing happening to this graph right here? It's going up 1. Do you see any nice, neat points that we could like make that happen on? So how do we make this function go up 1? Take the y-axis first. I like taking the y-axis too. So it starts. Actually, I'm going to make that. There's a point there, right? Actually, let's look for are there any other nice, neat points? Oh yeah, but they already dotted those. Do you see any more other than the endpoints? Yeah, yeah. Up 1 over 2, and then backwards as well. That might be it, right? So I think this function's technically like x squared, but maybe it's even like 1/2 x squared, because it looks like the normal quadratic, just wider by a little bit, wider by twice as much. Usually the quadratic goes there, right? Usually you go, here, wait, I'm going to just do a little expanding. Usually the quadratic goes over 1, up 1, and then it goes over 2, up 4. Usually a quadratic looks like that. What? Oh, is it really? Oh, man. Well, I don't know what to do about that. Dot? Oh, it really is struggling to keep up. Let's find out if I can just disconnect and reconnect. On the screen, it's probably fine. So if you're watching this later, this is all for naught. Let's see if this helps. All right. So we've got like 5 nice, neat points. So what are we going to do with all 5 of those points? I know you can't see it, but maybe you didn't dot. Take every single point and shift them up 1. Is that faster? Okay, cool. And then you know what? We just connect those dots. Yeah? If it's not like exactly perfect or you have a little bit messed up lines, it's okay. But I think it's really important to hit those nice, neat points, because those are the only things you know for sure. Without them giving you the exact function, those are the only things you know for sure. So that's the best way to approach that. Not too crazy? We can do this one because we do have to ask ourselves the question, do we reflect it first? Or do we horizontally shift it first? Think about PEMDAS. Think about PEMDAS. Shift or reflect first? Multiplication comes first in PEMDAS? So I'm going to reflect it first. Oh. Yeah, I guess, dang it. You're right. I shouldn't have said PEMDAS. Because technically those parentheses aren't there, right? Technically those parentheses are like... I'm trying to think of how to... Technically those parentheses aren't there if it's like x. If the function's like x, right, then there's no parentheses. Or if the function's like that. I don't know. Here's why we reflect it first. Is this negative going to do work on that? Is this negative sign going to affect both of those things eventually? Okay, pick a function. Pick a function. Any function in the world. X squared, right? Well, now it's not x squared anymore. Now it's x minus 1 squared, right? And you got a negative sign on the outside because of that negative sign. Is that negative going to affect both of those two things?
Yes.
Okay. So we should probably do the negative. We do the negative first because we don't want to accidentally shift it and then not. Now on this one, it's not going to matter so much because it's a vertical reflection and horizontal shift, so it's not going to affect anything. But what you don't want to do is you don't want to like vertically shift it and then horizontally shift it and then flip it across the x-axis like this, when technically it's a reflection that's been vertically shifted and horizontally shifted, because the negative is going to affect both the up and the down, or the up and the left. And if your negative flip is going to affect where your function ended up, it's going to be real hard to remember, oh, it's a reflection across the axis of symmetry, or it's a reflection across the vertex, and not necessarily across the x-axis. It's a vertical reflection. And so we're going to reflect it first. I don't know. If you need to remember that, just reflections go first. This one doesn't have one, dang it. These two don't matter. Yes. It would look like, if it was horizontal, it would look like boop, 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 like that. It actually probably looked like that, to be completely honest, because that's a horizontal shift. Otherwise, you'd have to distribute it first. But we didn't talk too much about horizontal reflection. We haven't done a whole lot of horizontal reflection examples. All right, so we're going to reflect it. Same 5 points. Zoom in. Still tracking? Yep. This one doesn't get changed. This one does. This one does. 4 up, 4 down. 4 up, 4 down. And then after we reflect it, what do we do with that thing? This says move to the right because it's a little bit opposite of what you'd think. And so your final function, your h of x, is the red one. That one, it wouldn't have mattered which one you did first. But other ones, it might. Yeah, I'm pretty sure. Yeah, it wouldn't have mattered. If you would have moved it first, you would end up in the same spot. Now here, it really doesn't matter which one you do first because they're both on the same level of PEMDAS, even though there's parentheses. The parentheses aren't there. They're just like placeholders. Because if you had a regular linear function, I don't know, y equals x plus 1, and then you added 1 to the inside and you added 1 minus 1 from the outside, it would all do the same work. So the parentheses aren't necessarily there in every single function. Some functions, they are going to be there, like if f of x was the absolute value function. Now you've got some stuff going on. But that negative on the outside still would affect everything happening inside of it. All right, so which ways are we going? Based on these two shifts, we're going to the left by 1 and down by 1. And if it's something that's like this and it's kind of a little bit easier, then you are more than welcome, if you can handle it, to do them both in the same. You don't have to draw the 2 phases of the shift. If your brain can go left and down at the same time, then do it. So if you can go like this, doom doom dot, doom doom dot, doom doom dot, doom doom dot, doom doom dot. I'll even erase that. Super loud. All right. Zoom out real quick. Leave there. Erase all these. I might label vertical reflection to the right by 1. There we go. Is there no water bottle? All right. Anybody else have a problem that they worked on this weekend? What'd you say? Let's see. Oh, inverses? Yeah. And C is definitely the toughest one. And if you remember from class and just from doing these types of problems, I think before you start, so we're going to hit C, and before you start, you might not remember because I don't think we made a big deal of it, but there's kind of a way that you can know if you're headed in the right direction or not. Anybody remember, once you get to your answer, there's a way you can pretty much know whether your answer's at the right format or looks the same. Does anybody remember what it's going to look like? It's going to look really similar, right? Your inverse is going to look like something plus or minus something over something plus or minus something, right? The format is going to be really similar when you get this tougher problem. So if it were just 1 thing over 2, it would look like 1 thing over 2. So you kind of know if you're heading in the right direction if you end up there. And if you don't end up there, take a pause, try again. This one has that extra step that was tough that JT bailed us out on last time we did class. I think we did this one on the board, like on the whiteboard, and we were like, trying to explore what to do. So let's get started. First things first, we're gonna swap. I'll give you the easy step. I'm gonna swap y for f of x because it's easier to work with y's than it is with f of x's. We're gonna swap it back at the end, but just because it's way easier to mess around with a y variable than like a whole function notation, I always start by doing that. And then I'll let you call out the second step. That's the whole, the word inverse means swap x and y, right? That's literally like, if you were going to shorten the definition of inverse, that's the thing to know in your brain. It's a backwards function. You swapped your domain, or swap domain and range, which is super true too. Okay. So now we've got x equals y plus 1 over y minus 2. And here's where you have to do math, and it gets a little tougher. Any thoughts? We'll do the same thing we did last time, which is you just got to explore away until you can kind of see something happening. Okay. Why'd you do that? I'm not arguing with you. I'm just wondering how you need to do that. So you're going to like do that. Thoughts? Yep. Okay. Hopefully, if you just do 2 or 3 of these types of problems, maybe there's even one on that second review I gave you, you'll start to see it's the same method each time, even though this is the hardest type of inverse, this little fraction one. Cool with that?
I would press that 2x to the other side and minus y.
So you're going to go plus 2x and minus y, which is great. But what was the reasoning behind doing your correct step? So like that, kind of. Those will cancel. Those will cancel. Minus y. Factor out a. That's like the key step that you're trying to make happen, right? You are trying to turn 2 y's into 1 y. That's the only way to do it. There's really no other way to make it happen. And so now you got a y on the outside and x minus 1 on the inside. And last but not least, probably the most important. So y equals but like we did last time, that's not actually y. And it's especially not the same y from your original function, right? So if you've got your 2 functions, that's not y. That's technically like the x's from your original function. Now it's the y's because we swapped x and y. But in order to not confuse ourselves in that regard, we're going to actually label it what it is. It's not f of x. It doesn't have anything to do with f of x. It is some inverse function that will return x's for y's and y's for x's. And like we said earlier, does that look like it's a pretty similar format to the original function? A plus or a minus on the top, plus or minus on the bottom, something in each spot. It does look pretty similar. So definitely the hardest type. The last step 3 or whatever, was put f inverse x back in. That was, if you were like looking at the textbook steps, those were the 3 steps. Put in y, switch x and y, and then once you get y by itself, put in f of x, or f inverse x. Cool. Is there any way to check whether that's right or wrong? Hmm? Yeah, it's going to be really annoying. Oh, you do it again? Sure, that's one way to check. He said you could do it again. You could invert that new function. Totally true. Or the way the book actually like taught before we even learned how to do an inverse. There's a specific way to use this bottom function and this top function to check and see if they're inverses of each other. They're not the same. There is a way to check and see if it's an inverse or not. What? That's like kind of checking, but because you can't check you could make a table and see if they flip flop, but that won't check every point in the world unless you're going to make the biggest table ever. You could draw it on a graph. That one's hard because they're the reciprocal functions, and those are the ones that look like this. And again, even if you drew it on a table, you can't check every single number because there's infinite numbers in the world, right? But there is a way to check and make sure these are exact inverses if you wanted to. Or if they gave you 2 functions, they said, are these inverses? Okay. No, that would be to check if it's a function or not. You could take f of the inverse, and it's supposed to give you something back. Likewise, you could take the inverse of the function, and it's supposed to give you something back. But do you know what this is not the bot. This is the... Yeah. Oh, yeah. Like the composing a function, putting a function inside of a function. And it's supposed to... It will give you back x if you do that, and you do it carefully. I'm not going to do both ways, but I want to just do one way real quick. So I'm going to take f of the inverse. I just want to check and see because this one's going to be annoying. So box plus 1 over box minus 2. And then what's going inside of that box? That new inverse function. 2x. Oh my goodness, never mind. I don't want to do this. I didn't realize how annoying that was going to be. Because now you have to like get common denominators and all that. Holy moly. Well, 1 is not 1. 1 is actually x minus 1 over x minus 1. And 2 is 2 x minus 1 over x minus 1. And so that's the same thing as 2x plus 1 plus x minus 1 over x minus 1 all over 2x plus 1 minus 2x plus 2. You do like distribute the negative 2 across over x minus 1. Like keep, change, flip? Yeah. I'm going to get rid of the things that go away though. Plus 1, minus 1. Oh, good call. I knew there was something else and I couldn't see it. So now we're looking like we got 3x over x minus 1 times x minus 1 over 3. The x minus 1s go away, don't they? The 3's go away. You're left with x, which is what we said we needed. Yay. We did it right. That check is way harder than just solving for the inverse, I think, actually, because keep changing. What's up?
I have a homework.
Oh, go ahead, dude. Let's do it. You're going to have to read it slow, though, so I can write it. Ready?
You have 1,643 decorative bricks delivered to your house and set down in your driveway.
Oh, you're gonna have to do a wheelbarrow or something. Yeah. Okay. Go ahead.
You have to move all the bricks to your backyard.
Okay.
Move a few bricks by hand and quickly decide that it will take forever.
Okay.
So you go buy a wheelbarrow to haul the west. You decide to pace yourself by hauling 7 wheelbarrows of brick. Full of brick each hour. After 3 hours, you
Wait. 7 wheelbarrows.
7 wheelbarrows full of bricks each hour.
So 7 wheelbarrows per hour. Keep going.
After 3 hours, you determine that you have moved 383 bricks to the backyard.
3 hours. You've moved. I'm gonna make this a point.
383.
383 bricks.
After 6 hours, you find you have moved 761 bricks.
Question before you even keep going. I want to label my x and my y. Or actually, I'm gonna draw it like this because it's good to see. I'm gonna label my x and my y. What's x in this case? What's your input? What's your independent variable?
7.
No, that's a number. So what's that called? What are hours called in the world? Yeah. That's what I was looking for. But yeah, per hour is fine. Time. And if you want to call it hours, that's fine. And what's your dependent variable, or what changes based on what time you're at? Bricks moved, yeah. Bricks moved. Okay. Just good to know. Okay, keep going. Probably that's enough information to get a function.
How many bricks per hour are you moving on the wheelbarrow?
Yeah. Bricks per hour. That's probably asking for the most common thing we ever find in this class. We found it like 4 different days. Slope. Is there a way to find slope based on the information we have that I've already written down up here? Absolutely. M equals y2 minus y1 over x2 minus x1. Or change in bricks over change in time is what it feels like. So I'm just going to use those numbers they gave us. And somebody with better math skills than me, I can do the bottom one, but I'm not very good at the top one. Somebody do that top one on a calculator or something for me. Can I get an amen on that so that we don't just keep going on with the bad number? No, you didn't do it. Somebody do that top thing so we don't keep moving with a bad number. Gotta sneeze, but I can't. Oh, does that divide now? 126 what? Bricks per hour, because it's over, right? Bricks per hour. Okay. So that was the slope. Man, I gotta sneeze, but I cannot. Forgive me if I sneeze in the middle of the problem. What's it ask?
How many bricks had you moved by hand?
Ooh, weird.
You started using the wheelbarrow.
Okay.
This value is the literal interest.
Yeah. So do we have, in this class we did learn the way. Do we know a way to find an equation? No. That's what we need to be careful about.
What kind of equation?
A linear equation. With the information on this page right now, more explicitly, the highlighted section, do we know how to find an equation? How? That was right. We already used the average rate of change, or the slope formula. Now we use point slope formula, and which of those 2 points do we use? Yeah, it doesn't matter, but that one's easier. That one's way easier. So y minus 383 equals 126, because that's our slope. So we're doing y minus y1 equals m. I did label m, yeah. X minus x1. And so x minus 3 do a little bit of math, like you said. You said linear or slope intercept, right? So let's find the slope intercept real quick. Y minus 383 equals 126x minus, ooh, crap. Is that 378?
This goes back to what you can find.
Plus 383? Plus 383? Y equals 126x plus minus plus 5? And so what was the question they asked?
Oh, how many bricks did you move by hand? Oh, vertical.
Asymptote.
No,
Or,
vertical
sorry.
intersect.
Yep. Good call. So how many bricks do you think we moved by hand?
5.
Feels like it, right? What's the time when we start moving bricks?
0
Yes. Plug 0 in, see what you get.
into X or Y.
Which one is time?
Oh, X.
There you go. So plug 0 in. So y equals 126 times 0 plus 5. So when... So y equals 5 in that case. So you have the point 0, comma 5 as a y-intercept. Which means when time was 0 with this wheelbarrow, 5 were already in the backyard because that was when you started moving by hand. And you're like, this is going to take too long.
Hold up so I can get the point.
We're there. Which formula?
Function. Sorry.
The point slope formula?
No, the first one that we got 126.
Oh, sure. What were you thinking, Josiah?
I saw a question on the homework, and the answer, it was talking about population of moose in, I think it's negative population, so how does that work?
Was the answer negative?
Yeah, I got it right.
They were dying?
I don't know, they said it was negative population.
Is that like this?
I know, it was,
Were the moose getting hunted?
no, it was saying, so if the population of moose in 1995 was this, and then a year later, 1996, it was this, and if the population was like a linear equation, say it was the same thing, what would the population be in 2006? Well, it went down 2,800. I think in 95 it was 48.
The linear equation passed the x-axis and got into the negatives?
Yeah, it was like negative 26,000 something. I don't, and it was right.
So I put 0, so that's like this. I mean.
Oh, that is interesting. You can't have a negative moose. That's pretty funny.
I put negative, I got it right.
Well, good job. The math there is right. The thinking is, it does generate random numbers for your homework, so you don't have the same number as somebody else. And so if you got negative, but you got the same thing.
No,
You got negative as well. That's good to know.
Yeah, I just put the negative because when I put 0, it's like no.
Oh, could you erase the formula?
No? Brother, don't just copy my answers. This is your homework. I know it's your homework, but you just copy my answers. You're not doing any of the work yourself. Yes, ma'am. Negative moose is fine. In the real world, someday you're going to be an engineer, and you're going to have problems like that. And you're going to have to say, hey, what does that actually... and then I'll get to you, Georgia. What does that actually mean that you should report to the LBM or whatever, the Bureau or the BLM, the Bureau of Land Management? What should you tell them in that case? You should tell them, if we don't do something about this, guess what's going to happen? We're going to... That's actually happening up in Colorado right now. Elk tags. So elk tags for out-of-staters used to be like, I don't know, a couple $100, maybe $150, not even. And they've skyrocketed to like, I don't know, 3,000 because of that exact problem. Because they're saying, if we keep going at the rate we're going, we're going to be a negative elk in the next 2 years. And so we need to up the price to like 3,000. And then we're going to reinvest that money back into elk preservation and stuff. And so it's a real, I mean, the stats are real, saying, hey, we're going in this direction. Now, that one little homework problem might just be like, yeah, you probably should have been allowed to write 0 and get it right. There will be 0 moose. But if we're going at this rate, this is how bad it looks. Is a fair, the number is still fine to find in the real world. What's up?
How would you show that a function is not a one-to-one?
Is it
If you're not given a graph.
without the graph?
Oh.
That's a good question.
Because
Put it in a
that's
graphic calculator.
No, we don't have graphing calculators. How would you show a function's not one-to-one? Do you have the function?
Yeah.
Let me. I might have to see it and think about it. Ooh, I do know how, but I'm not gonna tell you. Okay, give me a function.
Okay, so f of x equals -2 parentheses x minus 1 squared.
Mm-hmm.
That's not 101.
How
Oh,
do
wait, no, I'm sorry, plus 3.
plus 3 is fine. How do we show that this isn't 1-to-1?
It's a parabola.
We know it's okay. We know the shape. So there's a ration out of this, which is on the day one of functions, the day one of this test. I said there's 7 functions you need to know. At the top of the page, it said functions you need to know. And if you saw this little 2 right here, then your brain should have said, "Oh, that looks." Now I know the shifts are going to happen. So technically, it's reflected. So like the parent function looks like this. This is extra review. Parent function looks like that, right? Reflection happens. That's the reflection. It's a little bit taller. Now it's a little bit taller. It's shifted to the right by 1. Now it's shifted to the right by 1 and still tall and still reflected. It's shifted up by 3. I know that's a lot of stuff happening, but that's what happened. Is it got a little bit taller, twice as tall. It got reflected, it got moved, and it got moved again. And so the final function would be that red one right there. Or I don't have any more colors. This would be the final function right there. One second. I'm going to make it pink or purple. There's your final function. In your brain, do you know whether that's 1-to-1 right now? Yeah, it's not, right? Because it doesn't pass this test right here. But that's not proof.
So you have to graph it?
No, I'm saying that's not proof because we didn't give numbers or whatever. There is a way to prove it. Without a doubt, it's proven. It's just kind of hard because you have to find like the perfect spot. And I don't know where that perfect spot's going to be yet.
So
Isn't
basically,
it
find where it like meets 0 on
Could we find that? I don't know whether it meets 0 at a good spot or not.
Wait.
Let's.
Isn't a function being 1-on-1 mean it can have like 2 x's having 1 y?
And so we just need to find any 2 in the world. We just.
Yeah.
Yeah, but we need to. If we enter a point, we need to find the other point where it's exactly the same. And so nice, neat points might be the better way to go. I don't know if the x-intercepts are going to be nice and neat, but we can try. How do you and it'll review us on x-intercepts, which is good. How do you find an x-intercept?
Put in a 0.
For what?
What? For
X-intercept is plug a 0 in for x. Y. So let's go ahead and do that. So the 0 for y. Everything else stays exactly the same. And then we just solve it like we did in the first test. Because now this is the first test problem. That's why we did the whole really hard section on quadratic expressions, not equations. So this is a quadratic equation. This one you need to know a little bit about the graph. You need to know a little bit about the x and the y intercepts. You need to know a little, like all those the shifts that could happen. This is a quadratic equation. This is what we did in test 1, which is just a quadratic expression. And it's that's why we spent so long doing it, because now we're in that now we need to know how to do it. And so what did we do here? This is we are finding x-intercepts. Even if they're ugly, I think they're going to be ugly, but that's okay. They're still allowed to be found. First move. Anybody see it? I would move the 3 because reverse PEMDAS. So we're going to end up with 3, negative 3, equals negative 2 x minus 1 squared. Second move. So now we've got 3 over 2 equals x minus 1 squared. Third move. Big ol' square root. Ugly number, that's okay. Last move. Square root of 3 over 2 plus 1. We've made a terrible mistake. Or I have. It's in here somewhere. It's in one of these lines that I messed up. Close. Half right. Plus or minus where? Right there and right there. Why there? Why did we add a plus or minus? Because we wrote, yeah. because we introduced, and it looks like an F. We introduced the square root. So we add a plus or a minus. That's like saying when you go to square root something, we don't know whether it was the plus or the minus doing the work. And so what I know now is I know 2 points, right? I know this is kind of weird, but I know 2 points that are absolutely on this graph. What are the 2 points that I know for sure?
Square root 3 over 2 plus 1.
Comma.
Comma 0.
And
then negative square root 3 over 2.
And that's a proof.
That's going to be ugly to write, but you're right.
Well, I know, but if we would have found a nice neat one, it would have been way easier. That's a proof because that it's not.
Oh, yeah.
Because now if you go to your function diagram, you've got a 0 in the range, y values. You've got, now there's infinite numbers in these function diagrams, but those are 3 of them. And you know what lines happen? What function lines happen here? That's bad. It's not bad for a function. It's still allowed to be a function. It's not one-to-one. A one-to-one function would be like if we were taking a test and I said only one person is allowed to make 100. Next best score gets a 99. Next best score gets a 98. This is a function which is more normal for a test, which is 2 people are allowed to get 100. That's okay, but that's just not one-to-one. That's not saying there's a unique grade for every person. Okay, that's a good question though, because that takes some reasoning. It takes some like rationing where I know you probably could have got the question right. You probably could have said no. But showing like where's the proof? How do I prove something for sure? That is a proof. And if you want to get even more proofy, then you would say like because you have 2 values in the domain that correspond to 1 value in the range, it's not one-to-one. And that's all you need to say. But that's plenty to say. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Everybody's here. Yay. Thank you all for being here. Take a cupcake on the way out if you want. If not, I'll share with my next class. 1A. The difference quotient. Yeah, it's that one's annoying, especially once if it's the other 2 are not too bad because they're not quadratics, but when you have 2 spots to put it in, the tricky part is you've got 2 spots and 2 inputs. All right, so I think the best way to think about it is these are 2 different functions. You got a red one and a purple one, and a subtraction sign in between them. And so I'm gonna do the red function first, and say if this is f of x, 1a, what is f of x plus h? What do you usually do with the thing that's on the inside of those parentheses? What? Yeah, but I don't know what x plus h is. What do you plug what in? It is not. Okay, if it were f of this is what always helps. If it were f of 4, what would you do? Into where? Yeah, so it's not a 4. What is it? It's an x plus h. And so what we're going to do is we're going to say, okay, everywhere I see an x, I'm going to plug in an x plus h. And then I see another x, and I'm going to plug in an x plus h. You see what I'm saying? Even though it's ugly. Okay, so then here's a question. The purple one, f of x. What is f of x? Okay. And then the easiest of the three, I'll make it green. What is h? It's not a trick question. It's just h. And now we plug those three things into our equation and just reduce if we can. So we've got the red one first. X plus h squared minus 4x plus h plus 3 minus, because there was a minus sign in the middle even though it's hard to see. The purple one, I'm going to put parentheses around it though because that minus sign is going to do some work to the whole thing. X squared minus 4x plus 3 all over h. But now you got to reduce it. Like you got to actually do the math. And so the hardest thing to do is that first term, which is FOIL. It's not just x squared plus h squared, right? You have to do the box method or the FOIL method or whatever for binomials, multiplying binomials. And so the first section you're going to get is probably, make this way some more. X squared plus 2xh plus h squared. That was from FOIL. Minus, and then you got the, so the first one we did FOIL. And then this one we're doing the distributive property. And so we got minus 4x minus 4h plus 3. And then we do another distributive property with the purple. Minus x squared plus 4x minus 3 all over h. And then you should see some really cool things start to happen. So notice anything inside of there that's cool? Do it. Which ones are alike? X squared? Where's the only other x squared? Those turn into 0, don't they? X squared minus x squared. You see another one of those? You see another one? So now we've got 2xh plus h squared over h. And there's one more thing. There's one more simplification you can make happen. And it comes from doing something that looks like this. What on the top looks alike? So divide by h. You end up with a h outside of 2x plus h. And see that h on the top and h on the bottom? And so you just end up with 2x plus h. If you're doing a problem that looks like this thing called the difference quotient, stuff better start canceling out towards the end. And if it doesn't, go back and check your FOIL or check your distributive or check your negative signs. But you're going to get like almost everything starting to cancel out. Cool. That's a good question. Anybody else got a question as they were studying from the weekend? If you walked in late, there's some cupcakes if you want some. Feel free to grab a cupcake or just one. Don't grab two.
For B, do we just assume that
It's a fun. Oh, what? Keep going.
squared equals f of x?
Yeah, I think that was just me being dumb and not typoing for both of them. I think I just got lazy when I was typing. I don't remember.
What's one function so horizontal?
Yes. 1-to-1 is the horizontal line test for a function. 100%. Or if they give you a table, you know what you're looking for? You know what you're looking for if they give you a table? For 1-to-1, it's y values. So you would look at that and you'd be like, not 1-to-1. For functions, it's x's. And that makes sense if you think about the horizontal line test as a test. Pick any 2 points. Like call that one 4, 2. Call this one like -2, 2 or something like that. If you think about that, where they are on the graph, if this is the whole graph right there, that looks like about 4, 2, -2, 2. What just repeated there? The y value repeated. So if you think about like the horizontal line test existing on a graph and what it does to the two numbers. And the same for the vertical line test. If you think about the vertical line test, it would be x's repeating because they'd be in the same spot on the x-axis. Any other real specific ones that are challenging? Let's see. Domain of, oh, yeah. When you see the word domain, when you see the word domain, you're going to be looking for two things really. What are you looking for? If you ever see the word domain in a problem, without even looking at the problem, I know I'm looking for two things. A number over 0 is bad, or is bad. And if you get a number over 0, what do you do? Okay, maybe not if you get a number of 0. If you have a division sign at all, what do you do? Bottom. Careful. Does not equal 0. And if you get a square root, what do you do? The inside of it, the whole inside, greater than or equal to 0. These are called domain restrictions. If you don't, I don't always do this, but maybe I should. If you don't have either of those two things happening in your function, what's the domain automatically? Yeah, negative infinity to infinity. If you don't have any of those things in the domain and it's a domain question, just jump straight to negative infinity to infinity. But you asked about C. And C's got it, both of them. So which one do you want to do first? It doesn't bother me. You can. It doesn't change the answer, but you got to do them both. You want to do the fraction or you want to do the square root? Yeah, it's a little easier. So we'll do the square root first. And so we said the inside has to be bigger than or equal to 0. And then we solve for it, which means x has to be bigger than or equal to -2. And on a number line, I do it both ways because it just makes your life way easier. So on a number line, what does that look like? You go to -2, you color the circle in, and which way is it got to go? To the left or the right? To the right. Okay. And interval form, you do bracket, -2 to infinity. But we're not done because we have to do the other condition too. So what was the other condition then? The whole thing, right? So the square root of x plus 2 plus 1 should not be 0. Cannot be 0. It would be really bad if it was 0. And we solve for that. So what do we want to move first? Probably move that 1 over. And then square both sides. We end up with -1 times -1 is +1. So x better not equal -1. Nope, nope. Yeah. -1. That's a little weirder of an answer. I'm going to check and make sure just to be careful. Go back up to the problem. Plug in -1. What's -1 plus 2? +1?
I got the same thing.
Yeah, but I think it's totally allowed.
Mm-hmm. I don't know. Wait, square root of 1.
Oh, here's why it's allowed. Wait, x. What'd you say?
Square root of 1 is 1.
Square root of 1 is 1 plus 1. Is it allowed to be -1? If you plug in -1, you get -1 plus 2, which is 1 plus square root of 1 is 1, plus 1 is 2. That's totally allowed. So what? Now let's just like ration it out if that didn't work, or if we checked our answer because of those extraneous solutions for the square roots. If you remember back to that first day ever, we said you have to check your answer when you're working with square roots, which is kind of why I went back and checked my answer and working with square roots. What number would make the domain or the bottom equal 0? Is there any number you could plug in that would make this equal 0? -3 plus 2 would be -1. Square root of -1. What's the square root of -1? That would be I. Square root of -1 is I. Can this square root ever be negative? Can a square root ever kick you back a negative number? No, I don't think so, right? The graph of a square root looks like this. Never going to be negative here or here. It's all positive all the time. And so there's no domain restriction on the square root. Even though we checked it to make sure, we still checked it because if that would have been a positive number, we would have been out of luck. Or if it would have made it positive and worked, we'd have been out of luck. But as it stands, that's an extraneous solution, or that's an extraneous. It's not even a solution because it's not equal to 0, but I don't know. I don't know what you would call that. It's extraneous, but it's not a solution because we were saying not equal 0. So we double checked it and we said, okay, well that doesn't necessarily matter. And so our domain, there's no restrictions from the square root side of things. And so that's our domain. And if the square root would have kicked us back a number that was in that, we would have had to exclude it and like put a little circle there. So if the square root would have kicked us out a number, we would have had to put a circle like at 3 or something and done that. But because it didn't kick us out a real solution, we didn't have to include it, which is actually pretty interesting. I'm glad you asked that question.
So do we just put like no solution for the green?
No, because we weren't looking for a solution per se. That's why I was like, it's not a solution. We were looking for a restriction. Okay, so if you wanted to write no restriction, you could totally write that. But the question's never going to ask you find the restriction for each possible find the domain restriction for each possible domain restriction. It's not going to, it's just going to ask you what's the domain? What are all the x values that this is allowed to be? Really, that interesting part comes in from right there, this line, where we don't have a number that a square root's ever going to kick us out of -1. Impossible. So if I were being careful, I could have seen it right there, but it's still worth going through it. And if you remember back in test 1, we said the only problem, you should check all your work, especially if you get done early, but the only one that you have to check is square root problems or radical. Radical questions were the only ones that you had to go back and check. Cool. That's a really good question. Thank you for asking. Anybody else got any other test questions, review questions, homework questions? Yeah. Uh-huh. Mm-hmm.
I was gonna ask so to find the slope intercept point, who's the point slope point first, right? So the first one would be y minus 5 equals 3 parentheses x minus
2.
2.
Mm-hmm.
And you
And then you just
just solve that.
distribute the 3, carry over the whatever's attached to the y, the 5. But knowing it in both forms is good. If you're looking at linear equations, being able to report the point slope and the slope intercept is really, really valuable. And the slope by itself, if it gave you 2 points to be able to find the slope. Those are really the 3 main things there. Any other types of questions?
I get confused on the graphs for domain and range. Can you do a for me?
Domain and range for those graphs?
Mm-hmm.
Does it ask for them?
Yeah. It says use the following graph to determine the function's domain.
Excuse me. Oh, like this one? 2? Yeah. All right, what does domain mean? Bless you. Yeah? Bless you. Domain pretty much. Okay, domain, yeah, let's do this. Domain pretty much means x values, right? Or a question to ask yourself would be, what can x be? Bless you. So what numbers could x be?
6.
Could it be 6? 1, 2, 3, 4, 5, 6. Yeah? Could it be 7 though?
7.
Right? X is not 7. And it's not negative 1, 2, 3, 4, 5, 6, negative 7. So what's the smallest x value that it can be? Negative 6 right there. And the biggest one is? So our domain is negative 6 to 6. Range is a different question, but the same concept. You go to the smallest y and the biggest y. The only problem is it's not like you don't go to the endpoints. Domain, pretty much you always go to the endpoints. Range, you don't have to go to the endpoints. If you were to turn it sideways, though, they would look like endpoints. If you were to literally to turn your paper sideways, then they would look like endpoints on the for the range. Rotate it clockwise, if that's what you did. No, you turned it upside. It's upside down.
Either way.
So, I don't know. I can't rotate my screen, but if you're to take your paper and rotate it this way, so that the positive y. So rotate it this way, so that the positive y is on the right and the negative y is on the left. Kind of like the x is positive on the right and negative on the left. Then you could see what's the smallest y value of the whole function. Y value, not x value.
6. Is that 6? Wait.
I think you're upside down. Okay, here's a better way to do it. Draw a straight line in your brain or use your pencil and work your way from the negative infinity to positive infinity and stop when you hit your first thing.
0.
Boop. 0 is my first thing, right? So 0 is my first thing. And then keep going and stop when you hit your last number. I don't care about those endpoints anymore, right? I'm caring about the y-axis. And my tallest number on the range is
5.
Pardon me. And so it's kind of like the exact same brackety thing, but up and down instead of left to right.
And then you use the U when you have a jump, right?
You use the U when you, like in the next one, we'd have to use a U. So the next one would be left to right. So your domain would be negative, I think that's 3, to positive 3. And your range would be
0.
to,
Infinity?
are those arrows? Infinity would be if there were arrows. Well, yeah, I know it is. So what's the tallest number this red line hits? Almost. Does that red line ever actually hit 5?
No.
Because they're open circles? So it actually hits 4.9999999999999 forever?
So you wouldn't just like do a 5 with it.
You would do a 5 with the parentheses. Okay, 5 with the parentheses is the same thing as 4.99999999999 forever.
Oh.
Right? But because we can't write 4.999 forever inclusive, because it goes on forever, we say 5, but don't include 5. But include every single number ever right up until 5.
Thank you.
You got me sneezing. I said you got me sneezing now. Sniffling.
You're making my eyes water.
No, that's fine. It's because it's cold outside and then it's going to be 90 degrees and then it's going to go back to being 50 degrees. What's up? No. Yeah, it could be point slope. It could be slope intercept. It doesn't have to give you the equation of the line. It could give you 3 points and say, here's a point, here's a point. Find the slope. Then you find out perpendicular parallel from that slope, and then you use the third point to cross. So no, it could ask it in pretty much any form. But you know, in order to find a line, you have to have at least two things. Either 2 points, a slope and a point. That's it. Did you get this for the other one? If you went ahead and did it? Oh. I was just saying since we were there, I went ahead. Any other questions? What you got? Oh, that's what you got? Cool. Any other questions about the test coming up this week? All right, everybody should make 100 then. Yeah. What? Number 8? Oh, nice. Yeah, that's a good one. All right, average rate of change is kind of like something, even though it's not exactly the thing, it's very, very similar. Average rate of change is very, very similar to what concept? Yep. The only difference is average rate of change can apply to a squiggly line, and you can take a point, take another point, and find the, if it were a line, what the average slope would be. Whereas slope is an actual slope. Like, here's a line. What's the actual slope? Like those two purple lines might be exactly the same, but average rate of change is saying find the average slope for a red squiggly line, and slope is saying here's the linear function, find the exact slope at every single point. But the way you calculate them is exactly the same. That's just the pictorial difference on what we're actually looking at there. And so in order to find slope, you need 4 things. You need y2, you need y1, you need x2, and you need x1. Well, we've got 2 of those. How are we going to find the other 2? You can say it.
Okay, so you just do 3 of x, and then you plug in x1 and x2. You get 2 different equations, and those are your y's.
So you take this green one. Say, well, what is f of x1?
3 of the square root of 3 times 3.
I'm going to say I'm going to make it even cooler. F of 3. And then you plug it in. 3 times 3 is square rooted. And what about f of x2? F of 12. 3 times 12 is square rooted. And technically these are, I should label these as one extra thing at the very end. Y1 and Y2 for our brains to be like, oh, now I know exactly where these things go. And so if I was going to plug all those new things into our original formula, it'd look like 6 minus 3 over 12 minus 3, which is 3 over 9, which is 1/3. So your average rate of change is equal to 1/3. So plug and tug is the answer to what you're like. The thing you needed to do was plug in those x's.
Are you gonna put this online?
Yes, I'll post this and the video.
Then Iris calendar.
Oh no!
Congrats.
Dang it! Which one?
Purple one. So I think it's 06.
1, 2, 3, 4, 5. Oh, it definitely does look like 6. Thank you. Good find.
And then
Oh, and the other one too? 1, 2, 3, 4, 5. No, those are 5.
a -4.
Oh man. You are right though. Good save. Way to go back and check your work. Taking a test and you just turned it in early and you missed both of those because you missed a little bit and you knew how to count. Just being careful.
Can we do a 7?
Mm-hmm.
Specifically D.
Yeah, B is the tougher one because it's got two independent things happening. So when you're doing adding and left and right shifts, it doesn't matter which one you do first. And when you're doing, yeah, I guess that's it. Or if you're doing horizontal and vertical stretches, it doesn't matter so much what you do first. But when you're doing, what's it called? Two different things. So you got stretches, reflections, and shifts. And that might be it. It totally matters what you do first. And so, I don't know. Do you have any inclinations as to which one, if you reflect first or you shift first? I'm going to go to the very last page of the thing because it's going to give us the order for all of them, not just these two. Reflect. Feels like PIMDOS does some work here, whereas reflection is a multiplication by a negative number, -1. And shifting is just adding or subtracting a number to the values, right? So yeah, I'm going to reflect it first. If you go to the very bottom of the transformations, we didn't do this in class because I don't think there was an example after it, is what I was actually interested in. Vertically stretch horizontally. Oh, maybe that's why. No. This is what I was thinking. I was like, it didn't talk about it specifically in the book, and that's why I was talking about this with someone earlier. Yeah, it doesn't say explicitly like the order when it says you can combine them. And so I was totally okay with people being like, well, which one do I do first? Because these are just examples. It said like when you're doing this first vertically stretch by A, but it didn't explicitly say reflect, even though it's in the same spot, the -1's on the outside there. And I was a little like, I don't know, if I were writing this or looking through this, I might add a little section that says here's the order that you should do things in, because our text just didn't have it. I was looking right now just to see if I was right, and I think I was. Is that an order? Nope. Yeah. So I mean, the best hint that the book gave you, even though there is an order and you should be careful, was that one? No. Sorry, I'll get to it in a second. I just really wanted to see if I'm missing something that they wrote. No. Yeah, is this first vertically stretch and then vertically shift? Yeah, so I guess reflection should have gone in. So it should say first vertically stretch and reflect, and then vertically shift. Likewise, first horizontally stretch and horizontally reflect, and then horizontally shift. And then it does say this is just nice. Horizontal and vertical transformations are independent. That's true. So it doesn't matter which. So in this problem, it actually won't matter, which is nice. But it's still important to do the multiplying things first and the adding things second. And even though it doesn't say reflections here, reflections are the multiplying things because it's a -1. It's like -1 times. So we'll do the reflection first. So we reflect it. That's on the outside. Outside is always vertical. And so we're going to pick some nice, neat points. There's one. There's one. There's one. There's 2 more on there. Y'all see you need 2 like good points there. Okay, right there and there. And then the first thing I'm going to do in red is I'm going to reflect it vertically. I'm going to reflect it across the x-axis. So I'm going to end up down here, way down here, way down here. So that's a vertical reflection. And then this -1 tells me to do what with it? It's on the inside, so it's horizontal, and it's flip-flop, what you would think. So we go to the right by 1. So 1 dot there, 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 and we just connect the dots. So that blue one is h of x. On this, it'll be bigger on our test, but no, you don't have to. I'll be able to tell pretty quickly if it's like down, over. Yeah, that's right.
If it was -2 of f, it would condense, or would it get like?
If it was -2 of f, it would have gotten a little skinnier. Yeah, 100%. Or technically, it would have gotten taller. It would have appeared skinnier though. So technically, it would have multiplied by 2 on the y, because on the outside. So your question was if it was -2f like that, it wouldn't have gotten you. It wouldn't appear. You wouldn't skinny it. You would make it taller, because on the outside is vertical stuff, right? And that's on the outside, and it makes sense. So it's twice as tall. So that would be like making you twice as tall. So where it used to be, I went down 1 right there. Now in the same amount of time, I'm going to go down 2. And where it used to be that I went down 4 right there, in the same amount of time, I'm going to go down 8. So now it does look skinnier, but it's because it got taller.
So you multiply
Times 2 on your
point.
each point is getting twice as tall if you want, or twice as vertical. So see how that's 1 away? Now it's 2 away. It used to be 4 away. Now it's 8 away. It got twice as vertical, which because it's a vertical stretch. The horizontal stretches would make it explicitly skinnier automatically. If it was on the inside and it was a 2, it used to be 2 wide. Now it's 1 wide. It used to be 4 wide. Now it's 2 wide. It would look like that. It might actually look the same. I don't know for sure, but.
So you're saying if -2 times x?
Yeah. Yes, or +2. The negative is a reflection, different thing. I'm just saying if there was, if it was on the inside and there was a 2x on the inside, so it would have been like 2x minus 1.
No,
2x minus 1. Well, 2x minus 1. Then it would have been twice as wide. Mm-hmm. Yeah. We got to move fast, though. All right. Inverse. if you had to remember one thing when you see the word inverse, that's it. You switch x and flip or switch x and y, 100%. But wait, I don't see a y here if we're doing C. Yeah, so rewrite it. And then apply the inverse, which is. And now you have to kind of, it's more of a, it's kind of a puzzle. But the good news is the answer to the puzzle is going to look a lot like what you started with. Like we kind of talked about that in class. I know it was really short and at the end of class. But if it looks like this, then your inverse is going to look, nah, I don't want to write equals. Your inverse is going to look like boop, 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 boop. It's going to look really similar. If it was 1 on the top, it would end up with 1 on the top. It's going to look really similar to what you started with. The numbers are going to move around. The signs are going to move around plus and minus, but it's going to look almost the same. So let's go real quick. Anybody know the... Just because you don't like fractions, nobody likes fractions, let's not work with fractions. Let's get the fractions out of here. What you do to one side, you have to do the other side. Any math thoughts now? Don't do it. No. Be careful. I know it's hard. And that's not because it's right. It's just because we're running out of time. And it's how we're going to get there. You could get there -1, do some stuff, and be fine. It's just going to add a couple steps. There's a very, very mathy thing that just appeared for the first time. The distributive property? Yeah. So we got xy minus 2x equals y plus 1. Now, how are we going to turn 2 y's into 1 y? That's crazy. Move it over. Yeah, the factor them out. They have something in common and you got to factor it out. But in order to do that, we got to get them on the same side. And so I got to go minus y plus 2x. And so now I've got x, y, minus y equals 1 plus 2x. And now we can do that step. What's in common? We're going to divide out a y from both terms. We're going to end up with a y on the outside and what's left on the inside if we do that. Divide the first term by y, you're left with x. Divide the second term by y, you're left with -1. Now last but not least, y is equal to 1 plus 2x divided by x minus 1. And does that look like the same? Oh, we're not done. I almost boxed it. We need to switch that y for the actual inverse. Let's zoom out real quick. Also, we went really fast. We did that same exact problem in the 9 o'clock. If you want to watch the YouTube video and watch the first one, we did it a little slower. I know we did that kind of fast, but those are the steps. And I know it's weird to be like, hey, you're allowed to subtract that one first. You really are. It's just not going to get you there as fast. You're going to have to move you're still going to end up having to distribute. You're still going to have to figure out how do I get all the y's on one side and everything else on the other side. Here was us doing it earlier. If you want to look at it real quick, maybe. I thought we did it. I know we did it. Oh, yeah. And then we even checked it earlier, which was really annoying. But when you plug the inverse into the original function, it better spit you out x. And so we did that to practice composing functions because that's the composite function. So we did the little box method thing where you open up a box and put the inverse in. And then we had to get a common denominator, cancel a lot of stuff out, and we did end up with x. It was really annoying for that specific function, but we did check it and got it, proved that it was the inverse. All right, y'all have a great day. I will see you on Wednesday. Once again, feel free to come to the 9 o'clock. If you don't have a 9 o'clock class, we're just answering questions at the 9 o'clock as well. I'll send a reminder about that this Tuesday night.